Hello, my name is Maverick Madison, and this is Lab 2 for EEE120. First, I'm going to go over to 1-bit 2-to-1 mux. Here, we take an inputs A and B with a selector S and produce an output Y. We know that muxes are arranged by 2 to the power of n, where 2 to the n is the number of inputs, and n is the number of selectors. And then 1 in the 2-to-1 mux represents the number of outputs. This schematic is actually pretty simple. Our selector input will mimic both the A and the B inputs. Therefore, whenever the selector is set to 0, it will mimic whatever truth value the A input will have, and that will be stored as our output. However, whenever the selector is set to 1, it will mimic the B input, and it will output whatever our B input is set to, whatever its truth value is. So let's go over some examples. As we can see, input A and input B are both 0, and our selector is 0. So since our selector is 0, it will represent our input A, which is 0. Therefore, our output is 0. And whenever we turn A to 1, our output will be 1. And we can turn B on, it will still have our selector representing our truth value of A, and that will be our output. However, whenever we turn our selector to 1, it will represent our B input. So B input is off or 0, and we will get an output of 0. But whenever we turn the B input to 1, we will get an output of 1. And it's the same thing. If we turn A back on, but our selector is still 1, it is always going to be representing the truth value of our input B. Next, we have the 4-bit 2-to-1 mux. So this schematic takes two 4-bit inputs A and B and takes an input selector. And we have a 4-bit output of Y. This schematic, since it is taking two 4-bit inputs, needs to incorporate four 2-bit muxes to account for every bit, with the selector input going into each of them. Ultimately, this schematic has the same functionality as the 2-bit mux as we did before, in that our selector's truth value combined with either input A or input B will determine our actual overall output. So let's go over some quick examples again. So since our selector is set to 0, it's going to be representing whatever integer value A is going to be storing. So say we set our A input to be the number, say 6. With our selector being 0, we can expect our output to be the same as A, which is 6. And if we set B to say like 4, it will still output 6 since our selector is set to 0. However, if we turn our selector to be 1 and keep our B, say our integer is still 4, so turn the selector on, we will get an output of B, which is 4. And we can set A to whatever integer we want, say like 15, it will still output the B value since our selector is set to 1. This is the timing diagram for the 4-bit 2-to-1 mux. So just to look at some of the examples here, whenever we have our selector set to 0 and we have our input A being 3 and our input B being 6, we can expect our output to be 3 since the selector is 0 and it's representing our input value of A. Now say with our selector being 1, input value A being 3, input value B being 6, we expect our output to be 6 since our selector is 1 and it's therefore representing our input B. Next, we have an updated version of the 4-bit 2-to-1 mux in that it has incorporated some segment displays. This pretty much allows for us to ultimately get a better visual of what our schematic is trying to do through these bigger displays. Now, just a brief example of this in the flesh. Say we set our A input to be like 9. Since our selector is set to 0, it is representing our input value A, and that is therefore our output, which is 9, the value of our input A. And if we change B to be another input value, say like 3, it is still going to be 9 as our output since our selector is still 0, representing our input A. However, when the selector is 1, it's going to be representing our input value B. Since the selector is 1, it represents the input value B. So if we set our B value to like 4, we will get an output of 4 no matter what input A is, because whenever our selector is set to 1, it will always represent input value B. Next, we have the NUT-NEG schematic. This circuit takes in a 4-bit input A with two other inputs, invert and neg, with an ultimate output of carry and a 4-bit output of Y. As we can see in the schematic, we can see multiple XOR gates, we can see an AND, we can see an incrementer from the previous lab. As a whole, these gates allow for 3 things to occur when talking about our inputs. We can pass through our 4-bit value of A, we can perform the ones complement of A, and we can perform the 2's complement of A. Now first, let's just pass our input value of A to our output Y. In order to do this, we just need to keep our invert input set to 0 and our negate input set to 0, or we can keep our invert input as 0 and our negate input as 1. So let's do this. Let's set A equal to, say, like 5. And since invert is 0 and negate is 0, we pass through our input value of A as 5. And this will be the same if we turn negate as 1. It will give us the same output. Next, in order to perform the 1's complement, we simply need to set our invert input to 1 and keep our negate input as 0. So with this input value 5, whenever we invert it, set invert to 1, we get our 1's complement of A. Since the binary value of 5 is 0, 1, 0, 1, our output will be 1, 0, 1, 0 according to the 1's complement. Lastly, in order to perform the 2's complement, we just need to set our invert input to 1 and our negate input to 1. So when we do that, we have our input value of 5 for A, and we have an output value of B. We get B by performing the 2's complement by keeping the furthest to the right bit that has a 1, and then we flip the rest of the bits. So 5 would be 0, 1, 0, 1, and by 2's complement, that would change to 1, 0, 1, 1, which signifies the value of 11, which is B. Next, we have the AND add circuit. Here we have two 4-bit inputs A and B, along with input carry in, input add, and input pass. As we can see, we've incorporated a 4-bit adder and some 4-bit muxes into the schematic. And these are used in order to perform our operations we're trying to get, which include AND, add, and pass through. Firstly, when we have our two 4-bit inputs set to some input values, with all the other inputs being off, we should expect the schematic to compare each of the bits places using the AND gates. And as soon as all the bits are compared, we should expect a 4-bit output where the ones are all in the same places in the inputs. So a little example of this is, like, say we choose like 5 for A input and 13 for B input. We're going to expect an output of 5 because 5 in binary is 0, 1, 0, 1, and 13 is 1, 1, 0, 1. So those 1, 0, 1s are all the same. And we're only comparing the ones here because that's how AND logic works. So in the end, as an output, we expect 5 out of that. Now, when the add input is set to 1 and all the other inputs carry in and pass are set to 0, we should expect both input A and input B just to simply be summed up, and that sum is carried in our output Y. So whenever we're adding 8 and 7, we will expect an output of 15. And this is where carry-in can pretty much be used here. Carry-in increments our sum by 1. So as we can see, 15 plus 1 is equal to 16, but 16 can't be represented in 4 bits, so it changes to 0 since 16 can't be represented. So it just carries over back to start from 0 to 15. In doing this all through the 4-bit adder, we should expect any potential carry out or overflow, or even both, when adding accordingly and using carry in. Lastly, if we just switch the pass input to be 1 and either leave all the other inputs as 0 or turn all of them on, it will always just pass the input value that is stored in A as our output. So as we can see, with pass being 1, it just passes the input value of 8 into the output. And if we turn add on, nothing happens. And if we turn carry in on, nothing happens. And if we turn both of them on, nothing happens. It just passes through our input value A to our output. Finally, we have the ALU circuit. This circuit pretty much takes in several inputs where we have two 4-bit inputs, A and B. We have an input invert. We have an input arith, input carry in, and input pass. Alongside this, we have 4-bit output Y, output carryout, and output overflow. This ALU circuit incorporates all of the operations from the previous schematics all into just one. As we can see, we have our not negate circuit and our AND add circuit. For one of the first functionalities of the ALU circuit, when we have our two 4-bit inputs A and B, with the rest of the inputs invert, arith, carry in, and pass being set to 0, we expect our output Y to be the 4-bit representation of input A and input B. So we're comparing the ones of both inputs. So for example, if I set input A to 12 and I set input B to 4, we expect an output to be 4. Why is that? 12 in binary is 1100 and 4 is 0100. So that one that matches in the corresponding bits of both input A and B, that's our result in our AND. So 12 and 4, that gives us an output of 4. And also in the process of doing all of our operations, we can see that carryout and overflow do tend to change time to time, but they're really most important whenever we're just doing our arith functionality. But what this basically is doing for every functionality is it's just adding the inputs and it's just going to give us a carryout and overflow for each functionality. That's all. Next, when we set the pass input to be 1 with the other inputs still being set to 0, we will expect our input value of A to be set as our output. So when we do that, we have our input value of A, which is C, or 12, and our output is also 12. And if we change our value of B, that will not change. Our output is always going to be what is input A. Now, when only the invert input is set to 1 and all of the other inputs are set to 0, we expect a ones complement of A to occur, but this ones complement is going to be ANDed with input B. So with input A being equal to 12, whenever we perform a ones complement, that is equal to 0, 0, 1, 1. And whenever we AND that with the input value 4, 0, 0, 1, 1 ANDed with 0, 1, 0, 0, that gives us an output of 0 because none of the ones match. Whenever we compare every bit, nothing matches with ones. Our next functionality is when we set invert to be 1 and pass to be 1 with the other inputs being set to 0. In this functionality, we are basically performing ones complement on A again, but we are passing that ones complement into our output Y. So with 9 being 1001, we perform ones complement, making that 0110. And with the pass being equal to 1, we pass that binary value into our output Y. 0110 is equal to 6, and that is our expected output. The next functionality we perform is whenever we set arith equal to 1, and we keep all the other inputs set to 0. So whenever we have inputs A, which is 9, and input B, which is 4, and we set arith to 1, we will expect an output of 13. 13, which is D in hexa. And in the process of using arith and setting arith to 1, we should expect any sort of carry out, any sort of overflow. And this is where we can actually include carry in our arith. If we set carry in to 1 with arith being 1, we will increment our output by 1. So in this case, 13 changes into 14 whenever we set carry in to 1. Our next functionality is when we set arith to be 1 and pass to be 1, and carry in and invert are both still 0. And what this does, it pretty much just passes our input value of A. So since A is equal to 9, we get our output of 9. And we can turn carry in on for this and nothing will happen. All it does is it just passes the input value of A to our value of Y. Our next functionality of the ALU circuit is whenever we set invert to be 1 and arith to be 1, and the other inputs are set to 0. Now, what this functionality does is we are taking the 2's complement of input A and we are adding it to input B. So, for example, we have input A being 9 and input B being 4. We take the 2's complement of 9, which is 1001, changing to 0111, and we are adding 0111 to 0100, and that gives us a value of 11, which is also B. And when we do this, we can also turn carry in on. This will increment our output. Now, for the last functionality, we set invert to 1, arith to 1, and pass to 1. And what this is doing is we are getting the 2's complement of input A, and we are simply passing it to our output. So in this case, we have input A being 9, and that is 1001. When we take the 2's complement of that, that changes to 0, 1, 1, 1, which is equal to 7. And as we can see as the output, we have 7. And if we turn carry in on or off, it will not affect anything. Here are all the timing diagrams for the ALU circuit. I can't walk through all of them since it would take up too much time, but this has been Lab 2 of EE120. My name is Matt Metz. Thank you.